So let's me remind you what we're doing. So the vision is we'd like to ask what are the possible zero temperature states of matter with a net charge density. And we described last time several cases that are well understood in weakly interacting theories. Those are superfluids, Fermi liquids, and Wigner crystals. But we said that it seems that there are experiments and materials that can't be described with that framework. And so we'd like to try to broaden our mind and understand what kind of systems you can get in general, and in particular strong coupling, to answer this question. You know, this is analogous to, you could ask the following, sometimes people ask the following question. You know, physicists who were all born on the moon. Would a physicist ever predicted the liquid state of matter? Okay. But he said, well, you have a bunch of particles. If the kinetic energy wins, it's a gas. If the potential energy wins, it's going to be a crystal, a solid. Okay? And a liquid is a very strongly interacting regime where both the kinetic energy and the potential energy are playing equal roles. And it's theoretically would have been very difficult to predict it. Okay? So that's the same game we're trying to play, right? We're trying to ask, are there phases of matter that our weakly coupled intuition would find difficult predicting? Okay? That's the name of the game. And the tool we're going to use is holography. And what we derived last time is that in a holographic setup, if you want to put your boundary quantum field theory at a finite density, then what you need to do is have an electric field in the bulk going out. Remember, again, the interesting physical question always concerns low energy degrees of freedom, okay, the dominant low energy degrees of freedom and the ground state. And in holography, as hopefully you know, I'll check in a minute. So stuff that happens close to the boundary is the short distance physics, and stuff that happens a long way into the bulk describes the low energy physics. So how many people have not heard this statement before? I gave you the chance. All right. So, okay, so then what we want to do is the charge density appeared as a UV boundary condition, and now we have to solve the equations in the bulk to find out what the low energy physics is. So in this lecture we're going to start thinking about this question, okay? You've got some theory of gravity in the bulk, you insist that there's some electric field at the boundary, and you want to understand what the interior of the space-time looks like, okay? So what's the zeroth order question? Actually, I'll tell you what, before I go there, what's the analogous question with no density? Okay, so the analogous question, if you're in the vacuum, okay, then two things that could happen would be that the theory confines, or that it doesn't confine. Okay, when it confines, there's a mass gap, and when there's a mass gap, that means that the space-time actually ends at some point, right? Because when there's a mass gap, it means you cannot go, there don't exist excitations infinitely far at infinite arbitrarily low energies, and so there's a gap, and roughly that distance is the mass gap, okay? So the space-time just ends, and there do not exist any low energy excitations, okay? That's the nature of a mass gap, all right? Whilst if it doesn't confine, then you'll get something like ADS, which has excitations down to arbitrarily low energies. So we want an analogous question to that, but we're asking now with finite density. Okay. So there's some stuff, it's not the vacuum. So this is the only difference between high energy physics and condensed matter physics is this, okay? We want stuff, we're not in the vacuum, right? We're not in the particle accelerator with, you know, a few particles, okay? There's going to be macroscopic Avogadro's number of particles, okay? That's the nature of condensed matter physics. Okay, so the new ingredient here, the zeroth order question, zeroth order question is of course, where does this flux come from? Okay, if you have some flux at infinity, clearly there has to be some charge in the inside that's creating the flux. Okay, so where does the electric flux at infinity come from? And so there are basically two possibilities. Okay. So one is that there's just some charged matter sitting here in the bulk. Okay, so option one is that the charge is in the bulk. And option two is that actually there's a black hole horizon here at the inside, and all the flux, all the charge is coming through the horizon. Okay, so option two is that the charge is all behind the black hole horizon. Okay, so to draw a picture, this would be some bulk, and there's just a bunch of charged matter here. The source electric field, and option two is that the bulk ends with a black hole, an extremal black hole, right, with 0 temperature, and that all the flux is just coming out of the black hole. Now, in this case, so in this paper, we gave some names to these two cases, okay, which we'll try to justify in a bit. We call this case cohesive, and we call this case fractionalized. So I'll come and try to justify those names in a moment. Okay? This notion of fractionalized will connect with something that came up, the word fractionalized that came up yesterday too. But before we get there, we should also say, when we have some stuff in the bulk, there are two possibilities. This matter in the bulk that's carrying the charge could be bosons or it could be fermions. Okay? And we already saw yesterday how bosons and fermions can carry charge. So if this matter here is bosons, then we're going to get something that's called a holographic superconductor. And if it's fermions, we're going to get something called an electron star. Okay? So we'll talk about, we're going to sort of go through this diagram over the next half an hour or so. Okay? But first let me say that this distinction is actually somewhat analogous to this distinction of confinement or deconfinement. Okay? So in words, so when you could think of the deconfined phase, so you have some Yang-Mills theory, okay, and you write down a Lagrangian in terms of gluons. Okay? In a deconfined phase, the basic excitations of the theory are the gluons. Okay? And in the confined phase, the basic excitation of the theory would be glue balls, okay, which are bound states of gluons. Okay, the gluons are confined together. And so, roughly, you can think of the gluon. The gluon would be like, it's just F, okay, it's the field strength, whilst a glue ball is a long string of many Fs, all many gluons that are bound together. Okay, these are operators. Schematically. So this is called the operator for a gluon, and this is the operator for a glue ball. It turns out there's an analogous thing here, that when the charge is carried by degrees of freedom outside the black hole, you've got gluons and you've got quarks, which are charged, right? And so when the stuff is behind the black hole, it's as though the charge is carried by quarks, and when it's outside the black hole, it's as though the charge is carried by mesons. Okay, that's the sort of analogous thing. So let's write that down. So this distinction, okay, between these two cases is actually a refined version of confinement. And I mean this in the following sense. Okay? Confinement is a statement about what happens to the degrees of freedom in a system. And now we're asking what happens to the charged degrees of freedom in the system, okay, which is a subset. And so what happens is the stuff outside the black hole these correspond to short operators in the quantum field theory. So, for example, if we have, that might be things like trace phi squared, trace psi squared. Okay, these are the bosons and fermions, and they're charged under this U1. These carry a charge, right? Whilst the stuff behind the black hole that's when the charge is carried by long operators. So, in the quantum field theory. And so those could be things like trace, I don't know, phi squared, f, psi to the 20, f squared, phi squared. You can make very long single trace operators. Now, I'm actually saying this in case some of you are familiar with, there's some papers by Minwala and Hartnoll and others that describe the confinement as a Hagedorn transition in field theories. But this may not be familiar to many people. So let me say it again. So these, right. So basically these guys are like the glue balls. These are like mesons, okay? So if phi is a quark, then trace phi squared is a sort of a meson, like ground state. And these are the operators. Let me say it again. So these fields that appear in the bulk, they all have a mass, right? Fields in the bulk have some mass. They have some mass squared, and that's connected to the scaling dimension delta of the operator in the dual theory. So the fields that appear in the bulk are light operators, and they correspond to these short states. Then you also have string states, okay? So string states in the bulk are very heavy, and they're made out of these very long operators, okay? And you can think of these as the black hole microstates, if you like. Okay, I'm getting a feeling this didn't make much sense, so let me just put a parenthesis on that. So it turns, if this was useful, this is one way of thinking about this distinction, okay, about whether the states are behind or outside the horizon. But in general, if that picture wasn't helpful, then you can just ignore it. Okay, so what I want to talk about now is, so suppose you've got some theory in the bulk, and you put it at some charge density, what determines which of these wins? Okay, what determines whether the charge is behind the black hole or outside? So to understand that, we need to understand some basic physics. So to determine outside versus behind the horizon, we do the following. Okay, so we need to remember about screening versus anti-screening. Okay, so let's remember that electromagnetism screens. Okay, so as you know, that means the following. Suppose we've got a bunch of charges, some positive and negative charges, and then we apply an electric field. Then the charges will separate, right? The positive ones will get pushed over here, the negative ones will get pushed over there, and these charges will create an electric field that opposes the electric field that you impose from the outside, right? So electromagnetic charges screen, right? On the other hand, gravity anti-screens. So now imagine you have a bunch of masses, and we apply a gravitational field. Okay, all the masses just fall down the field, right? They fall to the floor. So all the masses will go here. And the masses increase the gravitational field, right? Because they gravitate, right? So charges tend to reduce external fields, but masses will increase external gravitational fields, right? And of course, this leads to instabilities, in particular in the early universe. Right? That's how galaxies form, right? You start with a uniform state of matter at the beginning. If there's a very small heterogeneity here, then it attracts more mass, it then in turn attracts more mass, and so it clumps and forms galaxies, right? So the fact that gravity anti-screens is very important, and you know it very well. Okay, so now let's think what this means for these charged black holes. Okay, so let's say we start with a charged black hole. Okay. Now, what we want to see, okay, so we're trying to determine which of these is the ground state. Okay, so let's say we start with a charged black hole. Now, if we have some charged matter in the theory, so charged matter will be pair produced by the electric field. Okay, it'll undergo Schwinger pair production. And so there'll certainly be some probability of finding a positively charged particle there and a negatively charged particle there. Okay, just particle and antiparticle just pop into existence. And now you want to ask, what happens to these particles? Okay, so these particles have a mass and a charge. So they can have mass m and charge plus minus q. And now, basically, these particles will experience both of these tendencies. Okay, so in particular, they both have a mass. So according to the mass, they both want to fall into the black hole. Right? That's the anti-screening. But according to the charge, one of them will get attracted to the black hole, and the other one will get pushed away. So roughly what you expect is if the mass of the particle is bigger than its charge, they both just fall into the black hole and they'll be gone. Okay? If that happens, this guy wins. Okay? However, if there exist particles in the theory, in the bulk, that have charge bigger than their mass, then the positive charge is eaten by the black hole, the negative one gets pushed out, and because it turns out ADS is like a box, it sort of bounces back and forth and stays outside the black hole. Okay, so, right, so if gravity wins, so that means that Newton constant times the mass is bigger than the Maxwell constant times the charge. Just roughly. Okay, this is the number. You have to do this. You have to do some calculations to do this precisely. But this is the idea. If gravity wins, then both particles fall into the black hole. And that means the black hole is stable. And so in that case, you land here. Now, in the other case, if electromagnetism wins, then the black hole is discharged. Right? Because in this picture, imagine this black hole has a bunch of negative charges. If the positive charge falls in and this minus charge goes out, the charge of the black hole gets reduced. Okay, its mass goes up, of course, but its charge will go down. And so this appears as an instability of the black hole. And so there, the endpoint is the matter outside the black hole. And often the horizon is completely neutral. So now this is actually pretty interesting. Let's go back to the CFT, to the quantum field theory point of view. And what does this mean? So remember that this field, this charged matter we're describing, is described by some field phi in the bulk. And that field phi is due to some operator O in the quantum field theory, right? So what this criterion, and remember that the mass of the field is the scaling dimension of the operator, and the charge of the field is just the charge of the operator, okay? So that roughly gives us an answer to the question, which we can phrase as follows. Okay, so let's do the following. Take a CFT and put it at some finite charge density. CFT with a holographic dual, of course. Okay. If there exists an operator O in your CFT such that the dimension of this operator is roughly less than its charge, okay. Remember the mass is the dimension and Q is the charge, then JT is carried by this operator, which means that this field phi, which is dual to O, right? There's a bulk field phi, it's dual to O, is condensed, let's say, outside the black hole. Again, this is, at least, that's the idea. Now, this O could be a boson or it could be a fermion, okay? And so if it's as we said, if it's a boson, then this charge outside the black hole, how the bosons carry charge, well, they just condense, okay? And you get a condensate. And if it's fermions, you just get a Fermi surface sitting outside the black hole, okay? So Fermi surfaces that gravitate, okay, are called stars. Right? So, in particular, a neutron star is just one humongous Fermi surface that is warping space-time. Okay? And so these are charged fermions warping space-time, and that's why they're called electron stars instead of neutron stars. Okay? But the equations that describe them are the same ones that you'll find in the astrophysics textbook under neutron stars. Okay? You just have to add some charge. Okay? So I put condensed in quotes because fermions don't really condense. Okay? But they're there in the space-time. So let's let me just write that down. Okay, so if O is a fermion, then the quanta of phi, the bulk field in the bulk, form the gravitating Fermi surface. And that's called an electron star because basically the same equations as neutron stars in astrophysics. You know, same, they're not the same because it's charged and they're in ADS. Of course, in astrophysics, most of the time doesn't happen in ADS. Now, if O's a boson, then phi condenses and it breaks the U1 symmetry spontaneously, right? Because it's a complex field, and so when it condenses, the phase will have a vev, it will point somewhere. Breaks U1 spontaneously. And so this is sort of like a superfluid or superconductor. Now, it's important that, might be a good point to think about what this means. So this gives you a criterion. So you could translate this statement as follows. Take a CFT, put it with finite charge density. If there exists a bosonic operator whose scaling dimension is roughly less than its charge, then the ground state of that theory will spontaneously break the U1 symmetry. Okay? When it has a holographic dual and so on. That's a non-trivial thing, actually, which it'd be nice to have a field theory proof of this. So here's a question. Does there exist a CFT proof or of some statement along the lines of that if there exists a bosonic O whose scaling dimension less than its charge implies that the finite density ground state spontaneously breaks U1. Spontaneously breaks the U1 symmetry. Now, you see, this is a different way. So normally, when people talk about superconductivity in condensed matter physics, the theory they have in mind is something called BCS theory. Okay? And BCS theory involves a certain quartic interaction between electrons. And there's a certain coupling. Okay? And so, what determines whether a conventional electron system becomes superconducting or not is whether the electron-phonon coupling is strong or not. Okay? That's some weakly interacting picture. There's some coupling that's either strong or weak. But you can only use this picture when it's weak. This is a criterion for superconductivity that's phrased without reference to any weakly coupled theory. It's very much in the spirit of what Pedro's been talking about. The data of a CFT is just the operators, their quantum numbers, and their scaling dimensions. Okay? So if you like a strongly coupled picture of superconductivity, you want to say something becomes superconducting if, and then you want some statement that only depends on your CFT data. Okay? That's what this is. All right? Things become superconducting when you put them at finite density if a certain property in the spectrum of operators is satisfied. Okay. So
isn't it the same? You know, the CS theory is that there is this level of as well.
Say again. If this applies in BCS, if there's a BCS version of this, is that? Well, so good. No, so BCS doesn't involve a CFT anywhere. So this you just can't. It's not the right language for that case. So yeah, indeed. So CF. So BCS there you. Actually, no. I'm sorry. No, actually, no. It should be. That's actually a good point. So actually, here's the way of thinking about BCS. So let's say you've got some free fermions and relativistic fermions, and this is the dispersion relation. Okay, and so if your chemical potential is energy momentum, okay. So this is the chemical potential. So if you go through the origin, then you fill the Dirac sea, but there's no density, right? This is the point JT equals 0, and this actually would be CFT. Okay, and then adding a chemical potential just means that you shift it up here, and you fill these states. Okay, these are fermions that then populate these states. So actually, you could think of BCS starting from this CFT, I guess. That is true. And then the operator, exactly. And then so in this case, the operator would be psi. Okay, psi dagger squared. So these are two fermions, which indeed has a low dimension. So actually, it's a good. I haven't actually done this exercise, but yeah, that's right. So it would be nice to completely reformulate BCS in terms of this language. No, that's right. So you could. But you see, so this Polchinski, this RG flow, that's more about the theory the theory here, the low energy theory, zooming into here. And well, this is more sort of starting with the CFT data. Yeah. Okay, so just again, a tangent. If it didn't make any sense, that's fine. So, but the point I'm trying to make here is this is it's a strongly coupled criterion for superconductivity in the sense that it only depends on the CFT data. It doesn't depend on any Lagrangian or weakly coupled description of the theory. What time did I start?
Yes, 30 past.
How fast? Any other questions so far? Good. Okay, so now we've, I guess I've erased it. So we have these two possibilities. The charge could be inside or outside the black hole. I've just described what happens when it's outside. So when they're bosons, you get some kind of superfluid because an operator condenses, and when they're fermions, you get some kind of star. Okay. Now, if I was giving these lectures 4 years ago, I would have spent the rest of the time talking about these two options. Okay. But I'm not going to do that this time. So let me say, so electron stars and holographic superconductors, they have an interesting phenomenology. Meaning if you start calculating conductivities and so on, some interesting stuff happens. Phenomenology. But as phases of matter, in terms of classifying phases of matter, they're more or less conventional. But in terms by which I mean, in particular, that the holographic superconductors are a special case of superfluids. Okay, so they broke the U1. And electron stars, it turns out, are a special case of a Fermi liquid. By which I mean that they obey the Luttinger theorem. And remember, what the Luttinger theorem says is that basically all the charge is in Fermi surfaces. Okay? So basically you can think of a star, a neutron star, is basically many Fermi surfaces, one inside the other. Okay, roughly, and that's what these stars. So what this means is that it's the following. So you have this picture, and you have some electrons here in the bulk. And what you can think of basically is that at every radius inside the star, there's a little Fermi surface. Okay, so this picture is in momentum space. So at every, right, in fact, okay, and what happens is it gets smaller as you go to the boundary. So what a star is, it's a collection of Fermi surfaces, and the Fermi momentum, right, which is the radius of this Fermi surface, gets smaller towards the boundary of the star, and it just goes to zero at the boundary of the star, so and the Fermi surface just disappears. So that's what a star is. And so if you add up the Fermi momentum, the volume, sorry, of all of these Fermi surfaces, it equals the total charge. That's what this Luttinger theorem says. So, just to repeat, when the charge is outside the black hole, in terms of classifying states of matter, it doesn't look, it looks more or less conventional. Okay, you either get a superfluid or you get Fermi surfaces. Okay. So the most unconventional case is when the charge is behind the horizon. Okay, so now we're going to focus on the case where the charge is behind the black hole. objective is to find new phases of matter, like qualitatively, not just quantitatively, but just qualitatively different phases of matter. Okay, so charge behind the black hole is the most novel, so we're going to focus on that. So again, just before we go to black holes, are there any questions about these stars or superconductors? Okay, so one more time. I should have a print that makes this picture. It's saving a lot of time. Okay. So remember, what we need to find to understand the IR is this low, we want to find the geometry in the interior. Okay? So what we want to do now is we need to find the black hole solution to Einstein's equations and see what it looks like close to the horizon. Okay, that's what we want to do. So for that we actually need a theory in the bulk. Okay? So many things like n equals 4, ABGM, what you have to do in the bulk, of course, there are infinitely many fields in the bulk because there are infinitely many fields in the operators, single trace operators in the theory. So what you need to do is what's called a consistent truncation and try to find a way to set almost all of them to 0 and just focus on the fields that you care about. When you do that, a typical action that you get looks like the following. So some Lagrangian for the bulk will typically, there'll be an Einstein term. Now there's a Maxwell field, so there'll be a F squared term. So that's the simplest thing you can get. That's Einstein-Maxwell, okay? And the correspondence constant. Okay. That's Einstein-Maxwell in anti-de Sitter space. But often it's interesting, what you often get is there are also some scalar fields. Okay. Let's think of this. So again, this is Einstein, Maxwell, ADS, and let's just call it the dilaton. I don't mean that it's literally string theory dilaton, but it's some scalar field that you often have in the bulk. The scalar field can come with potential, and furthermore, it often changes the kinetic term of the Maxwell field. Okay. So it turns out that in many consistent truncations of 2B supergravity or M theory in the bulk, this is the kind of action you get. Okay, it's gravity, electromagnetism, and a scalar field. Sometimes there are 2, 3, 4 scalar fields, whatever you want, but it has this general form.
So if you start from n equals 4, what kind of approximation do you do?
So there are many. So n equals 4, there are 3U1 symmetries. Okay, just rotating the S5 inside SO6, and so this Maxwell field is some angular momentum. So often, well, it's simple. Okay, let's say you just want to get let's get Einstein-Maxwell first. Okay, so the way you get Einstein-Maxwell is if you turn on equal angular momentum on the three orthogonal planes of the 5 sphere. Okay, so.
No, but my question in which approximations is the fact?
So it's not an approximation, it's a consistent truncation. So what that means is that you have 2B supergravity, the action in the bulk, that you can make an ansatz for the metric and the Riemann field that's consistent, meaning that it solves the equations of motion without sourcing any other fields. It's non-trivial to find these things, right? Let me say a few words about that then. You know, this is the original, as probably many of you know.
So classical subset.
Classical, yes. This is, well, at large n. So this is take classical 2B supergravity. And so let me give you an example of something that's not consistent, okay, which is actually what Klutzer did. Okay, so Klutzer, when they were doing this U1 compactification, they got it wrong. Okay, and that's because so again, the idea is this is a consistent consistent truncation. Of course, you know, for particular potential and particular z. So consistent truncation of, for example, 2b on ADS5 times S5. And so here's an example of something that's not a consistent truncation, right? So Kaluza and Klein, I think that one of them got it right and one wrong, and I don't remember which one it was. So there they wanted to have Minkowski space cross S1, right? And they wrote down the ansatz. The S squared is going to be 5. So this is, by comparison, 4, right? And then they had the circle, d theta, which is this S1, and then they put the gauge field there. Okay, that was either Kaluza or Klein's ansatz. Then they took this, and if you plug this into, they did the classical mistake of you can't plug your ansatz into the action. Okay, you have to plug it into the equations of motion, right? It's we'll all make this mistake once in our life, but you know, best not to do it publicly. So, right. So if you take the Einstein action and you plug in 5D, and you plug in this ansatz, you find that you get the Einstein action in 4D plus a 4-dimensional Maxwell field, right? And this was their idea to unify electromagnetism and gravity. However, if you look at the equations of motion, the 5D equations of motion, and you plug in this ansatz, you'll see that you won't solve the equations of motion. And why is that? And what you need to do is you need to include a dilaton there. So suppose you include the dilaton here, what will happen, and then you plug it into the equations of motion, you'll find something like box phi is, I think it's F, how's this go? Okay, this is in quotes, but I don't remember the formula, but it's something like this. An F there that looks wrong.
F squared.
Yeah, maybe, not sure. Let's say maybe something like this. And there, if F squared is non-zero, you cannot set phi to 0, right? Because phi 0 here gives you 1, and phi 0 there gives you 0. 0 is not equal to 1. Okay, so that means that you cannot set, it is not consistent to set phi to 0, right? Because you cannot solve the equations of motion, right? So when you reduce from a circle, you have to include this phi, and you get that phi squared there and some e to the phi type thing there. And that's the consistent truncation. So that's what you have to do. So if you want to start with 2B supergravity, and dimensionally reduce it on an S5, and this Maxwell field F is a lot like the Kaluza-Klein field A, you just have to include all the fields such that you consistently solve the equations. Right? So this is what you can do, and you get things like this. It's consistent. Okay? So in fact, on ADS5 times S5, you can actually get just Einstein-Maxwell, which you can't do in a flat space. Right? So again, if you ever make an ansatz, make sure you plug into the equations of motion, not into the action. Okay? Unless you know what you're doing. All right. Good. So, yeah. Does that address your question, more or less? Okay. So, there's a sector of, a consistently truncated sector of 2B supergravity, and therefore n equals 4 super Young-Mills, that is described by actions that look like this. All right. I think maybe I should write down. So the upshot here was that you need to keep phi for consistency. Alright, so now what do we want to do? We have to take the equations of motion following from this action and solve them and find the black hole solution. Okay, so I'm not going to go through this, but I'm going to tell you part of the answer. So it turns out that all that we really care about is we don't, we'll see next time, I'll show you, that to understand the low energy properties of the theory, you don't even need the whole solution. Okay? All you need is the near horizon geometry, okay, to get the low energy. So all the low energy physics is all in this near horizon geometry. So various people, I guess Blaise actually has done a lot of work on this particular theory. So what we now need to do is classify near horizon geometries. Okay, that's what the question has become. This setup, we need to understand what does space-time look like close to horizon. So near horizon geometry, these are extremal black holes. Okay, I'm at 0 temperature. So let's start with the easiest case. Let's start with just Einstein-Maxwell. So no scalars. So in Einstein-Maxwell theory, the black holes are called Horizon-Nordstrom black holes, and the extremal black holes are called extremal Horizon-Nordstrom black holes. And the near horizon geometry in this case is something called ADS2 plus, I'll write R squared. This is for 4-dimensional. If you want to be in type 2b, you can make it R3. This doesn't matter. That's in 4D bulk. Okay, so let me write. So this as a metric is ds squared equals dt squared plus the r squared plus the x squared plus the y squared. Okay, the near horizon geometry of extreme Horizon-Nordstrom black holes is ADS2, and we're doing planar slicing. Okay, that's what's appropriate in condensed matter physics. That means you get an R2. So people, you might have heard about these ADS2s in the context of attractor physics of horizons. But more generally, so actually it turns out this is a really very special and very interesting geometry, which we'll talk about at length next time. The reason it's interesting is because, let's to preempt what's coming. So let's compare that with ADS4. So ADS4 would look like this, right? T squared plus the r squared plus the x squared plus the y squared all over r squared. Again, people normally call this coordinate z, but we'll see why we're not doing that. So ADS, as you know, has a scaling symmetry, right? Where you scale t, r, x, and y goes to lambda t, r, x, and y. Okay, this case. But this guy, that's the UV, right? The UV is ADS4. With the IR, the fact that the geometry becomes this means there's an emergent scaling symmetry in the infrared, okay? Not related to what we put in the UV. We just solved what we did, but somebody solved many years ago the Einstein-Maxwell equations. They found a solution, they zoomed in on the horizon, and there was a new scaling solution, which was this one. And here, t and r scale, but x and y don't scale, okay? So there's an emergent scaling where time scales, but space doesn't, all right? And now if we think of this relativistic scaling as telling you, remember this tells you that your dispersion relations will be only goes like, the energy will go like the momentum, right? Because when you scale space, you have to scale time as well, okay? But this tells you that when you scale time, you don't have to scale space, okay? And that's going to be weird, because that means that you can keep the momentum fixed and go to arbitrarily low energies, which is basically like saying there's no kinetic energy comes for free. In this theory, you can give a particle as much momentum as you want, and its energy can still be very low. Right? So this is a very exotic scaling symmetry in the IR of these extremal black holes. Okay, we'll come back to that next time. Okay, but more generally, so the general near horizon geometry in that class of theories has the following form. So it's characterized by two exponents. So there's r to the theta minus dt squared r to the 2z dr squared dx squared dy squared over r squared. Okay. So this is what you get if you solve the Einstein-Maxwell-Dilaton equations near the horizon. And so this z, this is called the Lifshitz exponent. And this theta is called the hyperscaling violating exponent.
So is it fixed or is it a parameter?
Sorry?
Is it fixed?
So for a given v and z, it's fixed. They're both fixed. So it depends on the theory.
So how does your ADS 2 times R2?
Yeah, sorry?
How does ADS 2 times R2 come out of this one?
Yes, wonderful. Good. That's an excellent question. So ADS 2 plus R2 corresponds to theta equals 0, and c goes to infinity. Okay. And to see that, you actually have to do a coordinate change. So it's a different color maybe. So you don't have to write this down, just to illustrate. So if you let, let's see, what do you want to do? You want r to go to r to the 1 over z. You just do just a coordinate change. That'll take this z and move it there. And this one will stay the same. There'll be a z squared there. Now you take z goes to infinity and it just sets that to 0. Okay, so that's how you get this ADS 2 plus R2. So it is there. And that's why you can see it's weird, right? So for z, the Lifshitz exponent is the relative scaling of space and time, right? So that's saying that omega goes like k to this, let's get this wrong. K to the z. Okay. And these are both going to 0, right? So, yeah. So when you take z goes to infinity, it turns out that, k doesn't scale. Okay, now this is nice because, this is the general, more or less, the general near horizon geometry that you get in a big class of holographic theories. Okay, and so what that's starting to tell us is what the data is. Okay, so so again the question is, you're in a strongly coupled theory, you shouldn't think in terms of coupling constants and in fields. Okay, you should just think of data, and like operators, scaling dimensions. This tells us that holographically, the near horizon data for the strongly coupled theory is captured by 2 exponents. Okay. So now, in terms of classifying states of matter, we want to see what do these exponents do? Okay, what do different values of theta and z correspond to? Right? So the lesson so far, our question. So the original question about classifying states of matter. We then went to holography. And then from holography, we found out that the relevant data, the relevant low energy data, is z and theta. Okay? So those are the concepts in terms of which we should think. And then once we've got these concepts, what we're going to start doing next time, well, there's one more thing we want to say today. So next time, what do z and theta actually do? Okay, what do the states of matter characterized by different values of z and theta? What do they look like? Okay, if you made one in a lab, what would you see?
But this parameter they erase only if you use this particular consistent constitution. So what controls the fact that you can use this one, not another? Like symmetry?
Well, it depends on the theory. So different theories, different microscopic theories will give you different values of z and theta. And so what we're going to do is parameterize
No, but that's assuming you use this particular truncation.
Right. So this is sort of...
I'm saying that maybe sometimes you have to go outside this particular truncation, then you will discover some more parameters.
Right, good. So what's true? Yeah, okay, fair enough. So what you're saying, there's an extra step here. Okay, so we truncated from the original question to holography, and then in holography we looked at a certain set, a certain subset of solutions. Okay.
What is true is that as long as you're not changing the symmetries of the metric, then this will hold even if you change the contents of the Lagrangian.
I mean,
like if you add a mass term to
it's
the
true
vector.
that there might be crazier beasts out there that we just haven't thought about yet. But some large class of solutions, very reasonable things look like this.
But more basic question: how do you know the symmetry of the metric? Is it induced by the symmetry of the boundary?
No, they're not related. So any symmetry that you get here is some emergent. I mean, when you put in the chemical potential, the charge density, you certainly broken your scalar invariance, your conformal invariance, you've broken, you still have rotations, but you've broken a lot of stuff. And so if you get some scaling in the IR, that's some nice thing that you found that's come out of Einstein's equations, but it's not related to any symmetry that you had in the UV. So I want to say, in the last minus 5 minutes, I just want to say a few things about these Z and thetas from a field theory point of view. So I want to show that they're not that exotic. Okay. So they're unfamiliar, possibly because you may be used to doing relativistic calculations of relativistic quantum field theories where you don't break Lorentz invariance, and then obviously space and time always come together. Okay, but as soon as you start doing non-relativistic quantum field theory, these things will start showing up right away. So here's some quantum field theory intuition for, well, we're going to do both Z and theta, but today we'll probably just do Z, take 5 minutes. So let me do an example. Let's take what you might think is a very simple theory. Let's take QED in 2 plus 1. Well, let's not specify the dimensions. QED at finite density. Okay, so what's QED? As you know, QED is just the Maxwell field and some charged fermion. Chapter 2 in your favorite quantum field theory textbook. Okay, very simple. But now we want to put it at finite density, which means that we add mu times JT, and JT is something like, I always get it wrong. Yeah, don't hold me to the daggers and the eyes and stuff. Okay, but morally it's something like this. Right? That's maybe it's, I don't know. Okay. All right. So what's this going to do? So it turns out that this term really complicates life a lot, especially in 2 plus 1 dimensions. Okay. In fact, in 2 plus 1 dimensions, adding this term changes this theory from something that you all can solve to something that nobody knows how to solve. Okay. So what this term does, this will induce a charge density. And because the charged fields are fermions, what you expect that to do is to make a Fermi surface. So you're going to get in momentum space some Fermi surface. And so the low energy dynamics will be described by the low energy excitations of the Fermi surface. So remember, that's these particle hole pairs now coupled to this gauge field. Okay? And so it turns out that that's very hard. But let's go naively. So what's the first thing that you calculate? So for example, your boson, F, let me not worry too much about gauge invariance and stuff. So there'll be some two-point function to propagator for the gauge field. Okay? You know, in some gauge, that's something like that. Okay, you have a massless propagating gauge field. And so, you know, if you're going to start doing perturbative quantum field theory, the first thing you do is calculate the self-energy of the gauge field due to interaction with the fermions. Okay, so you do this Feynman diagram. That's your gauge field, that's the fermions, that's your gauge field. Okay? When you calculate this diagram, that'll be that term there. That's the self-energy. Right? So now you just have to. This is not the diagram, you know, in your favorite quantum field theory textbook, unless you're a condensed matter theorist, because this fermion, these are not relativistic fermions. These fermions have this extra term. Okay? So the propagator for the fermion that you have to use in this diagram has a Fermi surface, right? So it's something like I omega plus bf a minus kf. It has a propagator for fermion, remember, that's created out of a Fermi surface, right? The low energy excitations live on the Fermi surface, not at zero. Okay, so that's the propagator for the fermions. Okay, so what do you get if you evaluate this loop with this propagator? Okay, you can do it 1 page, half a page, not that much time. Okay, so what you find if you do that is that the sigma is equal to, in some low energy limit, mod omega divided by k, mod k. So again, that's this term in some low energy limit. So this has a name. Things like this. Sorry, these arrows are getting a bit messy. Okay. My apologies. This thing is called Landau damping.
Should be multiplied by mu.
By what, sir?
By mu.
So yeah, I've set. Yeah, there's some factors in there to make the dimensions work, of course. Okay, so let's go to Euclidean space and let's do that. So when you go back to Lorentzian space, right? So the reason it's called damping is because there's an I there and it causes a decay, right? Yeah. But schematically, it's at this form in Euclidean space. Now, what does this do? So then, when you go to low energies, omega fixed k and take omega to 0, this term will be bigger than that term, right? Because omega squared goes to 0 faster than omega. So low energies, this term actually becomes irrelevant. And so at low energies, the dispersion, the inverse propagator boson is of the form k squared plus omega over k. And when you balance that, this is a z equals 3 dispersion. So the dispersion, i.e. omega goes like k cubed, right? Which is z equals 3. So in this theory of QED, QED at a finite chemical potential, if you just do a naive one loop analysis, so at one loop, QED at a finite chemical potential goes in the UV. It has z equals 1, it's a relativistic theory, and when you flow to the IR, you have z equals 3. Okay. Not so different from the sort of thing these geometries describe. Okay. So it's reasonable once you break Lorentz invariance, z can flow. Okay, that's all I'm saying. The relative scaling of space and time doesn't have to stay the same once you break Lorentz invariance. So last 1 minute. Okay. So just as I know that there are probably some people in the audience that care about amplitudes and perturbative field theory, I just want to draw your attention that there's an unsolved problem, there are many unsolved problems in non-relativistic quantum field theory, okay? Even in this simple theory, right? So for example, what happens is that, okay, so this theory is not solved. In 2+1. And there are many ways of seeing the problem. One of them is when you calculate the fermion. That's the boson self-energy. There's also a fermion self-energy, which is this diagram. Right? And you'll find the fermion propagator gets an high omega plus k minus k. These i's are annoying. There's actually no I there. Okay, half of my mind in Euclidean space, the other half in Lorentzian space, but it doesn't matter. Well, this side doesn't matter. Actually, so you get an I here, and what you get is omega to the 2/3. That's the one loop correction. Okay? And what this is telling you, well, actually, we already saw it here. So this is telling you that the one loop correction at low energies is stronger than the tree level result. Okay? It actually has a more singular omega scaling. Okay? That tells you the perturbation theory is going to break down. Is going to blow up in your face. Okay, you cannot. The higher loop corrections are just going to get worse and worse. Okay, so this is more IR singular than that term. Okay, so perturbation theory seems unreliable. And so one question is not known. So for example, it's not known if z equals 3 is exact or not. So remember here we found the scaling, this one loop result gave z equals 3. It's not known if z equals 3 is exact to all orders. Okay, so it's been checked with 3 loops. Okay, I've heard people like doing 8 loops or whatever, so maybe.
There's some latest.
Sorry?
Latest.
Sorry?
On the latest.
Unrelated? Sorry, I can't hear it.
Simulation.
Oh, simulation? No.
The latest.
Sorry, again. It's fun. Sorry? Lattice? No, oh, okay, sorry. No. Good. You said lattice, right? Is that what you said? Yeah. Simulation? Yeah, okay. So, unfortunately, when you have a chemical potential, when you rotate this term to Euclidean space, you put it on a lattice, it becomes imaginary, and there's a sign problem with the simulation. So there are people working in that direction, but if you just take this theory as written, it won't work on a lattice. So my point is that once you go away from Lorentz invariance and you add just a simple term like this to a theory that you think you understand very well, it can very quickly get very difficult. Okay, that's all.
Questions, comments? I have a question. Is there a kind of limit the fact that if you do some perturbative corrections to the removal of the traction behavior, you to something more?
Right, so of course.
No,
good. Sorry, let me say two things there. So of course, there's like 20 years of work. I mean, it's not that people haven't tried many uncontrollable summations of things, but no, these. Yes, and actually this is. Okay. So indeed. So I think what you're asking is where does non-analytic stuff come from? Yeah. Okay. And so where it came from is that even here. When you do this, these are some fermions that you're integrating out. And you integrate it out arbitrarily low energy fermions, including ones on the Fermi surface. And so it's integrating out these sort of on shell, you integrate it out to light degrees of freedom, massive degrees of freedom, and that's why you've got this. And so one way that, and so people have tried to write down sort of self-consistent scaling. Right, so you can start doing some self-consistent stuff on this, but people haven't got it to work yet. But I should say that things are less nice than they are in Lorentzian theories. So there's just many more terms that can appear, of course.
Has anybody tried to put in two loops, for example?
Two loops? Yeah, yes. Yeah, no, people have done inflow loop. But they sort of they write down to a Schwinger-Dietzen equation that captures some subset of the loops, and then they resum those guys. But it's been shown that these are not controlled approximations. And I'm happy to talk more about it to anyone that wants.
Yes?
My question is about an electron fraction. How can the form because the particles are charged, so we have a very strong positive force?
No, that's a good question. So of course, astrophysically, we will not find any electron stars for the reason you said, right? That of course the electrons just repel each other, and right? But in ADS it's different, and that's because that the gravity is a bit different. So actually, that's an excellent question. So let's say we want an ADS, but we were just in flat space, which I don't even know how to draw. This is like this, right? So let's say you're in flat space and you do this pair, actually even a black hole, but yeah, you can take a black hole in flat space, and you do this pair production argument that I started telling you about, okay? And let's say that electromagnetism, okay, so gravity wins, it falls into the black hole, right? Now in flat space, if electromagnetism wins, you will discharge the black hole, the plus will fall in, the minus will get pushed out. But in flat space, it'll just go out to infinity, and it'll just, as you say, the electrons will just repel each other, and they'll dissipate out to infinity, and you'll lose them. Okay, so the endpoint will be a neutral black hole, and a bunch of electrons drifting off to infinity. But in ADS, where the picture's a bit more like this, when you have a plus and a minus, the plus falls in, the minus gets out to infinity, but then it gets bounced back again. So the ADS is like a box that keeps it in. So it's crucial that you're in ADS. So they do exist. So in ADS you can, the attraction of ADS can keep the star in place.
And then we get a strongly degenerate dynamic gas?
Yes. Yeah, so exactly. That's right. And so in astrophysics, these are called this thing called Oppenheimer-Volkov equation. Oppenheimer. Yeah, it is Volkov. Yeah. There are these Oppenheimer-Volkov equations that describe this degenerate gas, gravitating gas. So it's basically the same thing, but you add a charge to the electrons and you add a governable constant, and you'll find solutions.